unfolds. That is, it loses its tertiary structure while maintaining its secondary structure. And that partially unfolded version of the protein, what we can call the molten globule version, right? It's a glob, but it's molten, it's moving around, can reassociate with other copies. Remember, ensemble science, it's never alone. Other copies that also had unfolded and change its structure. It can move from being a globular domain to being a long fiber of beta sheets. So we're transitioning from a globular protein, a globular domain, to a fibrous structure. And this is the amyloid protein, which comes from the amyloid precursor protein. Sometimes it's called beta amyloid or amyloid. And it eventually forms these long fibers which stick together and form amyloid plaques in the brain. That's bad. One, this is needed. We need this, right? So if this is being degraded and going down this non-productive path, your brain's going to spend more and more energy making more of this because it needs it. But if there's something going on, some environmental or genetic or unknown factor that's unfolding it, in the process of trying to fix the problem, your nerve cell's like, oh, this isn't here, I need it, I'll make more. It's going to end up just making more and more of this. So it becomes this cascading cycle of damage. So cellular resources go to making this instead of keeping the nerve cell happy. It starts producing long fibers that distort the shape of the nerve cell and can eventually destroy the nerve cell. If you imagine like a little pup tent and you're trying to assemble a big long tent pole inside it, if you build a tent pole longer than the tent, it's going to rip open the side. And these long fibers will eventually stretch the nerve cells out and rip them open, killing the nerve cell. And then these fibers get released into the space between nerves, where they block the flow of nutrients, they block the flow of neurotransmitters and electrical signals, and the brain starts getting worse and worse. It's bad. Two of my relatives had very severe Alzheimer's and unfortunately lingered for years before their death. It's an awful disease. And the biggest problem is, and so all of this is about the amyloid fibrils. There's also another protein called tau, which has to do with microtubules, which has its whole other etiology of disease state. I don't want to get into that right now. What?
Mainly dementia.
Yeah, dementia stuff and all. Oh, it's great, yeah. So this is clearly a problem. I mean, hopefully we realize this is like horrible dementia and brain damage is a problem. But what's interesting to me about it is that it's so fundamentally different than how we approach any other problem medically. Let me give you an example. Early on in medicine, we decided, or we recognized that if something's going bad, get rid of it. Your limb has gone gangrenous, saw it off. You have a bacterial infection, have an antibiotic to kill the bacteria. You have cancer cells, take chemotherapy and radiation to kill the cancer cells. That strategy, destroy the bad thing, basically underlies all of medicine. And it will never solve this problem. Because if you destroy all of this, you don't have that, and it's essential for function, and you die anyway. So we need a new paradigm of medicine, because we're not trying to get rid of beta amyloid. We have to convince it to go back and fold the right way. We need medicine of folding, not medicine of destruction. Yeah?
Beta amyloid the name of the native protein?
No. It's the fragment that comes off. The full native protein is amyloid precursor protein. Because we discovered the amyloid first, and we're like, where does that come from? Oh, from its precursor. Brendan, what's up?
These misfolding diseases, is there like a critical amount of misfolded protein, or is it just one?
Such a great question, and unfortunately with Alzheimer's, the answer is we're not really sure. If anyone's been watching the science news, there was a study that came out about a week ago that suggests you can detect buildups of not full fibers, but oligomeric amyloid 20 years before dementia symptoms manifest. So clearly there's a critical mass, because it takes 20 years from when these start happening until you have noticeable dementia. But on the cellular level, it's much, so that's like the organismic level. On the cellular level, it's much less clear. We don't really know what the critical mass is or how it's brought about. Gets flushed out. Yeah.
So how is that, so is it,
Yeah, so let's talk about this. This is great. This is, I love, because we're actually getting into the fun stuff, like the interesting stuff, right? So here, just a little background on this. We don't really know what causes Alzheimer's. Like, let's get that out. But we do know some things that don't cause it. And maybe it's sad that I have to reinforce this. When I was a kid, there was this huge scare about aluminum cans and aluminum in your antiperspirant because it was confusing chicken and egg. When you have a long fiber, this structure, specifically these alpha helical domains sticking off the side, happen to bind aluminum pretty well. So once you have big fibers, aluminum grabs there, and so if you dissect an Alzheimer's patient's brain, hopefully after they've passed on, you see a lot of aluminum, and people were like, well, maybe aluminum is causing this, but it's backwards. These happen, and then aluminum comes. So you're not going to get Alzheimer's from aluminum. Okay. But we don't really know what causes it, really. There's some predictive factors, and we in America don't always like to hear these predictive factors, because the #1 predictive factor for eventual development of Alzheimer's is daily sugar intake. The more sugar you eat, the more likely you are to get Alzheimer's. Full stop. Period. Full stop. It's one of the best correlative predictive factors. We don't know why, but it is, and people don't want to stop eating sugar, so it's a big problem. Just to point out on that, because this is where I'm going to start getting all, as we get into more nutrition stuff, I'm going to be on my high horse. If I'm ever being a jerk, just like raise your hand and be like, we've had enough, Dr. Bonham, shut up. We eat way too much sugar in America. If anyone's ever lived in other cultures, like if there's a bell curve of sugar eating, we're way, way on the end. And we don't even mean to, but everything in America has added sugar. And every meal is huge with refined sugar. And it's just like, I encourage you to travel abroad and see a diet somewhere else in the world and be like, wow, I eat a whole lot of sugar. It's a problem. Some people, because of that correlative factor, there was actually a really controversial paper in 2008 that said Alzheimer's is diabetes type 3. And you know, I think that's conflating a little, because it's not a pancreatic misfunction, but it is clearly a sugar, and like there's some weird metabolism stuff tying into it. So that's the thing. The second biggest correlative factor is obesity, which ties into sugar as well. But yeah, the more obese you are, the more likely you are to have Alzheimer's. But again, we're rolling the dice, right? You can eat no sugar and be a healthy athlete and still get Alzheimer's. So there's something else going on.
I'm trying to remember this from years ago, so I might be totally off, but isn't there something where the cells in the brain don't have mitochondria? Mm-hmm. So they rely on blood sugar? Yeah. The brain is, it's not that they don't have mitochondria, but their optimization is slightly different. Yeah, the brain mostly needs sugar. But, and we'll get into this, so this is going to be fun. We don't need to eat sugar for that. The liver is great at converting fat and protein into sugar for the brain. So, like, you know, it's like one of the hardest things for me to grapple with, to give you a preview. You never need to eat cholesterol. Your body makes all you need. Damn if I don't love egg yolks. But we deal. So this is a problem. We can have some correlations, but we don't really have treatments. But one thing that we've noticed, and this ties to the sleep therapy thing we started, is that some people who have this problem, like you can measure that these things are forming in their blood, won't show actual physiological signs of dementia, or won't show them for a lot longer. And we looked into what is that. And we found a genetic correlate to protection from Alzheimer's, which is there is a protein complex in your brain, usually called ApoE, apolipoprotein E. And what ApoE is it's a garbage truck, or a garbage man. It looks for misfolded or denatured or partially folded proteins of all sorts. It's not specific to Alzheimer's, and destroys them. Pulls them in, gets them into lysosomes, they get destroyed. And so if you have hyperactive ApoE. You have a much higher expression level of ApoE in your brain and in your cerebrospinal fluid. Even though your body is misfolding these, rather than letting them progress to full fibers, you're trashing them. And so that's when you see these genetic risk factors for Alzheimer's. Most of it is based on this guy. The people at high risk for Alzheimer's don't really have a higher risk for Alzheimer's. We have no idea what causes the risk. But if they get it, they don't have the machinery to protect them from it. So that's the genetic risk factor. But that caused a really interesting thing. And this is where I need to pull up the paper. People would love to treat Alzheimer's or cure Alzheimer's, right? Like, let's be clear, there's no drug company that's like, I'll let a few $1 billion just, sit on the back burner. And the sad thing is that, this is a good example, Targetrin fails, high hopes dashed for a new treatment for Alzheimer's. Here's what happened. In 2011, a group studying mice showed that an already approved chemotherapeutic drug called bexarotene upregulated ApoE levels. That is, if you give this cancer drug, it's a chemotherapeutic, it kills cancer, but as a side effect that they didn't really understand why, it causes your body to start making a whole lot more ApoE. Which is impressive of its own, that they showed in mice in mice models of Alzheimer's disease, that it caused the amyloid beta plaques to break down, and it caused restoration, or at least partial restoration, of cognitive function in mice. Maybe during the break I'll pull up the paper. One way you measure cognition in mice is if you give them a Kleenex, they'll rip it into little pieces and build a nest, whereas mice with Alzheimer's will rip it up but forget what to do with it, so they just spread it everywhere on the nest. Sad, you know? But what they showed is that if you gave these mice with Alzheimer's this drug, after 2 weeks, they were building nests again. And this caused several drug companies to invest, and I'm using the correct term here, over $1 billion overnight into derivatives of bexarotene and new ways to do this. And one of them was this targetin. And the problem that soon became apparent, this was 2 years after the paper, is it does seem to do that in mouse models of Alzheimer's disease. It doesn't seem to do anything in actual Alzheimer's disease in humans. And it's a real bummer because people were super excited that this was like, this is it. Darn. Darn. But it opened up a new avenue because it got people interested in ApoE, and it got people interested in this idea of exactly what I'm saying in terms of new paradigms. It got people interested in this idea. Instead of looking for a way to destroy all beta amyloid, is there a way we could target a single folded state? Target this state, but not that state. Or even making, one of the newest drug efforts is an artificial chaperone. They want to see if they can build something that will help this fold back into the right state. But if people are like, why haven't we cured Alzheimer's? It's because fundamentally we're trying to answer a question we've never answered in medicine before. Every medical treatment is how do you kill the bad thing? And we can't. So, challenge. Maybe someone in this room's got the solution. If you do, hurry. I've got like 30 years.
It's kind of off base, but could you ever kind of treat like a disease with belly disease?
Oh, yeah. For example, one of my good friends actually has Sjogren's disease, which is an autoimmune disease where, especially like the tissues of the eye, like the tear ducts, get attacked by the immune system. So you like stop having tears and other stuff happens. And he treats it by giving himself hookworms.
It suppresses.
Yeah, because then his immune system is busy fighting the hookworms instead of attacking itself. So,
it happens to humans too, especially like my body attacks myself, like my hair follicles, because I've got colitis.
Oh,
so
yeah,
it happens
yeah.
to human a lot too.
yeah.
My hair follicle attacks.
Really common.
Yeah.
unfortunately. Sorry.
Doesn't stop him from taking voluptuous selfies of his
Is
hands.
that-
But so this is an example where we don't know a lot still.
I get you.
But the fundamental conceit that I really want you to get is that the tertiary structure was disrupted. And that loss of that final folded structure allows a different kind of structure to assemble that is very self-destructive, right? So it's a structural disease. Here's another great example. I want to talk briefly about cystic fibrosis. We were talking about all the fun things. One of my cousins has cystic fibrosis. It's very sad. He's 7 right now, and the odds of him living past 30 are not very high. So let's talk about it, because this one we know a lot more about. I think cystic fibrosis, from an intellectual standpoint, is fascinating. The idea in cystic fibrosis is that there is a protein, a transmembrane spanning protein called the CFTR, cystic fibrosis transmembrane receptor, whose only job is to move chloride ions, in and out of the cell. If we had found it before the disease, we would have called it the chloride channel. But we found it after the disease, so we called it the cystic fibrosis transmembrane receptor. But it's just a chloride channel. It lets chlorine go in and out of the cells. And importantly, it exists in our mucous membrane tissues. And we have to rely on osmosis. Which, a reminder of osmosis, if I have a low salt concentration here and a high salt concentration here, water will move to the high salt concentration to equalize the concentrations. This is how mucus gets wet. These cells regulate how wet mucus is and pull in the moisture from the bloodstream to produce mucus by playing with salt concentrations. If they need to pull moisture from the bloodstream to manufacture mucus, they raise their internal chloride concentration. Water that's in the adjacent bloodstream flows in. They swell with water, they produce mucus. So they produce mucus by regulating their chloride levels. In cystic fibrosis, this channel has stopped working. A lesson to take from this. We have to be very careful about physiological symptoms versus biochemical symptoms. There are at least 3 different causes for cystic fibrosis. The most common is that the domain that allows this protein to insert into the membrane has a deletion. So the protein is made, but just floats around inside the cell. It never gets inserted into the membrane, and so it can never do its job of moving chloride. That's the most common cause of cystic fibrosis. About 15% of cases, the protein is made and inserted into the membrane, but it has a single point mutation, a single R group missing that changes how it functions. And that's the one I want to talk about, because we're all about R groups right now, right? We should get a shirt like I heart R groups, or I histidine R groups or something. If we imagine the transmembrane channel is like a tunnel that chloride ions can flow through, our tunnel normally has a lid. Like if we imagine there's a thing, it has a lid. And the lid is normally open. What holds the lid open is that right here in this door jamb, there is a benzene ring. Specifically, there's a phenylalanine, and specifically it is phenylalanine 508. That is, if we started with the first amino acid being 1, and then the second, and then third, the 508th amino acid in this protein is a phenylalanine that holds this thing open. In about 15% of cystic fibrosis cases, it's been deleted. And the lid slams shut. And chlorine can't enter or exit the cell.
So when you say deleted, does that mean it's missing, like 508 is not there, 508 something else is not even a phenylalanine?
Yes, yeah. It's not a changed, it's a deletion. So
Okay.
if we look back at the genetic code, a whole codon is deleted.
Okay.
So a triplet is gone. Whole deletion. What happens then is that these mucus cells can't